Anyone remembers what loadings means in a PCA? We mentioned really quickly, but maybe somebody remembers. Loadings, weights, they call it. So again, the PCA object contains a lot of information. We access the variance explained by every PC, the actual matrix of the data, but also contains the loadings. So here I'm accessing the loadings for PC1. The loadings are the contribution of every gene for that principal component. So if we want to know the main genes creating the separation between normal and sleep deprived, that's the PC1, right? That's the one that's separating our condition. And we want to know, okay, what are the main genes contributing to that separation? I'm going to look at the loadings. So this long thing here is just accessing, sorting, and giving you the names of the genes. That's what it's doing, right? And I'm using the pipe. So I'm storing the loadings of PC1. I'm getting an absolute value. I'm creating the sorting, transforming to a data frame, adding the gene, and then I don't know I forgot what I'm doing here. But basically, what I'm trying to print out is the loading. So I want to know what genes are the ones that are contributing the most to our separation. And here you have them, and the loadings for each one of those genes. And the list, of course, continues. You have even more. I'm just printing the top 6. We don't do these often, but you could. You could explore your data in that way and figure out, okay, what genes are contributing for PC1, the ones that contribute the most. So those are the top genes.
So DBL here is the log 2 fold change, the last column.
No. It's the loadings. So there's no, again, our analysis has been done. Now we are playing just with, remember, we transform our data. And then we did the PCA. PCA is just you saying, their own analysis. There's no related to fold changes. There's no p-values, nothing. This is just the loadings of every gene. So this is actually PC1. Is a linear combination of every gene with a loading associated to every gene. So what I'm doing is trying to figure out what are the main genes contributing to the separation of PC1 that you saw in PC1. So these are the top genes. Again, it's not something we do commonly. I'm saying that it's doable. That's the only thing I'm showing.
Can we get the number? This is just the top 6, right? Can we get the number of the genes?
It's going to be all of them, probably. I don't think they filter for anything. You're going to have loadings of 0. If we go to the tail, right? I'm assuming R has tail. Oh, sorry. If I do... No, it doesn't need to be positive or negative expression. It's just doing a PCA. There's no expression here. So all genes are present, but with a tiny, tiny contribution. So, okay, Bonnie was asking yesterday. Okay, Bonnie, pay attention. How we can save plots. So there are different ways you can do that. So if we use ggplots, they have their own function that you can use to save plots. We can also use this own function that we can call the way that I prefer to save plots is using PDF. I don't know if you ever worked with Illustrator, with vectors, vector graphics. So vector graphics or raster images. So raster images are just pixels. You cannot modify them except if you do something special about it, right? So if you use vectors, so vectors, what it contains is information about the lines, the fonts, the text, and everything. So PDF allows you to save as a vector. So if I want to save a plot as a vector, later on I can modify it. I can open in a vector graphics editor, and I can change the font, I can type some text, and so on. If you have a raster image which has pixels, it's more complicated. I'm not going to be able to change the font. I'm going to have to put something on top of that font or do some manipulations that you don't need to if you can save the vector graphics. So I generally recommend to save it as PDF, but you can save it as a PNG, JPEG, or whatever you want to use. So the way it works is you open a device, they call it. So I give the dimensions. I think this is inches. So this is just a piece of paper size. And then I plot whatever I want to plot. I keep plotting, 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 and then I close the device. And everything between these two lines, whatever I plot, is saved in a document, which has this title. Right? This is a way to do it. You could do it that way.
So if I will save it in the PDF format, then I will not able to do any changes over it, right?
Yes, you could. Yeah, yeah, yeah. So that's what I'm trying to tell you. So PDF is going to store it as a vector graphic.
Okay.
So it's called scalable vector graphic. So you're going to be able to actually modify it. If you open this in Illustrator, you're going to be able to modify the lines, change the thickness, change the text, whatever you want to do with it. Illustrator is you need to pay. So Inkscape, I don't know if anybody works in Unix, probably you install Inkscape. I think it's called Inkscape. Is Inkscape the one that the vector graphic? I think, well, it's the one that you can probably use to modify these for free. I'm assuming Inkscape exists for Windows too. So we saw this plot earlier, which is the bar plot of the importance of each, or the variable explained by every PC. So if I run this, it doesn't give me any output because I save it directly to a file that it's here. So if I double click, here is the image that I just saved. So I'm asking you to save PC1 and PC2 in a single document. Give it any name. You can call it pca.pdf and save it as a PDF. Dimensions, you can give it or not. It's up to you. I think it's, what type of paper you use here? What is the size? A4? A4, okay. I think it's this letter size, the American letter size. So any problem saving the file? Did you create a PDF? Don't replot them. I don't know if you remember that we store every PC. We created an object that contained the plots. You don't have to replot them. If you go back, right? We store PC3 and PC4 in here already. So if you run already this, that's enough. You don't have to replot them. I'm assuming it's enough. So if I double click to the image, here we go. So now we have 2 pages, we have 2 different plots. A little bit too stretched, right? We should change the dimensions if we want to have nicer plot.
So there is no way to like
Please scroll it up and up.
click button kind of things to download the files. I mean,
Yeah. So if you want to download, well, I don't know if we should teach this. So Amazon charges for downloading stuff,
oh,
but
all right.
but yeah, you can. Again, we're going to share everything. So at some point, we're going to put everything available. PowerPoints, I'm assuming too, if you want them. I think at the end nobody looks at them, but the Jupyter notebooks will be available. If you do right click, and there's a section that says download, so you just can download it.
Yeah, don't download because maybe AWS will charge. Just
And you don't need to download it. If you have your own Jupyter notebook in your computers at some point, it's going to be in your hard drive. So you don't need all these operations on the left. Just added for fun this section here, which is plotting 3D-dimensional PCA. So it's possible thanks to the Plotly library. So if you try it, you're going to get some 3D dimension here, plot, and you can interact. So R is really powerful too when you can do interactive plots and things like that, but we are not going to explore it. But there's a ways to do 3D plotting in case you needed to plot 3 dimensions for whatever reason. Again, I don't think this is practical necessarily, but it's fun. Okay, so heat maps. That's something we talked also about yesterday. For that, we're going to use a library called Pretty Heat Maps, P-Heat Maps. The question is, what genes we're going to be plotting? For now, we are exploring. We don't know what genes are differentially expressed or not. They are in our object, but we haven't checked that. But what we can do is, for example, in this case, I'm picking the top 200 most valuable genes. Based on the, again, I'm not touching yet the analysis. I'm using the transform data. Basically, it's calculating the variance for every gene, ordered them, and I'm just picking the top 200s. I'm using this dot to say whatever output is going to be a data frame that I'm taking 1 to 200. That's pretty much what I'm saying.
one you have written 1
Or
to 200,
vector.
other you have written 0 to 200. How is that?
Oh, yes, sorry. Oh, that must be correct. Hold on. Is this a data frame? That's a good point. In R, they use index 1. The 0 doesn't exist as an index. So I'm not sure why I said that. Ignore it for now.
Disable when that hash in front of that, it means it's disabling.
Oh, yeah. So this is not a line of code now. This is just a comment.
Yes.
So actually, this should be, I don't think it should be a 0. It should be a 1 because in R, it's index 1, not index 0. But this is not going to run anything because it's just a comment. You're correct. So one thing, again, it's always good to explore what we're doing, right? So if, oh no, that's the one I want to do. So anybody knows what is this? So I'm not getting genes. Yes, but these are not gene names, right? This is the index position in our table. It's just where the gene is in our table. That's what it is. No, is the position in the table. Is the row. So the topmost variable gene is in the position 14,400 something. Because I'm going to need this to access the genes on the table, basically by position, not by name. Oh, I'm saying it here. So if you read it, it contains the raw indices of the topmost variable genes. That's what it means. So I'm asking what this section here does, basically. We used these brackets before a few times. And what we're doing here, remember, separated by comma. Whatever's in front of the comma, the first number you place here is the rows. Whatever you place after the comma is the columns. If it's empty, it means everything. I'm giving in the indices of the most variable genes. So you are getting only the rows for the most variable genes. So I'm just selecting our modified counts to get only those for the genes that I care. So those are the ones I'm going to be plotting. And this is just preheat map function telling everything we need to do, right? So I'm telling them cluster by rows, don't cluster by, don't show the row names, cluster by column, and explain the rest in a second. Just, we can plot it now. In this case, compared with the case we talked yesterday, right? We said that heat map from a paper was selecting genes that created the separation. Here we are not selecting genes creating any separation. We're just picking the top 200 most valuable genes. So this clustering is already telling us that a good clustering for our sample, just picking the top 200 genes. But this is typical, right? We generally present on papers a heat map with clustering for the samples, clustering for the rows, although again, I don't think this gives us any information. It's really hard to read, and we don't make any comments generally on papers about them. So I'm still not sure why we're still plotting them, right? And generally, just looking at, you already know that is a group of genes here, these clusters here that lower expressed for normal, and this is higher expressed by sleep deprived. So I don't know if anybody knows. Do you know what this part here means, a scalable row? Do you notice here? I'm expressing, or I'm plotting the count values log transform, right? That's what we're plotting. But why we get negative values? Doesn't make any sense. I don't have negative counts, even if you do the log transformation. So it is because we're scaling. Try to plot it without the scale. Say, so if you remove, right? Super hard to read now. I'm getting a completely different story here. And if you have a gene that is really highly expressed, it's going to be red, and everything else is going to be blue. So what we do with the scaling, oh, sorry, not this. Whereas we are, sorry, normalizing or z-scoring. You know the z-scores? So you're z-scoring the whole row in that sense. So these are z-scores actually, right? So you get the average of the row, right? So the average of the row is going to be 0, and the standard deviation is going to be 1 or minus 1, right? So this is what are you doing. So basically what you're telling here, I'm doing a really poor job explaining this. How is called the z-scoring system? Is normalizing? So you're scaling the row to have an average of 0 and a standard deviation of 1. That's what you're doing. So basically, 0 is the average of this row in expression. That way you can compare every row. If you use absolute values and you have one gene that scales 100,000 and the rest are values of tens, and you try to plot it, it's going to look like a red and everything is going to be blue. In a way of scaling, what you're doing, you're going to be able to compare the rows in that way. Standardizing the row. That's the word, right? So you get a z-score.
What are the bars over above the blue and the red line? What are those?
Oh, so these clades? Yeah, so this is a clustering. This uses a method of distance clustering, like a phylogenetic tree. So basically, no, you're calculating distance between samples in here and distance between genes here. Yeah, but it's related to the idea of phylogenetic trees, right? So you calculate the distance based on the expression, and you beat a cladogram on top to know how they close to each other they are. So basically, you have two big clades, and they represent the normal ones and the sleep deprived. And because we picked the 200 most valuable genes, we already know that that means that we have a good clustering.
And why is it so crowded on the y-axis?
On the left, because we picked 200 genes. Let's pick less, right? Yeah, so, my bad. I think that probably you already knew, but maybe I didn't explain it well. Every row is a gene. Every column is a sample. I mean, you have the names of the samples here at the bottom. We don't print the names of the genes because they wouldn't be readable. I mean, it's already hard to read this. Imagine having 200 gene names here. I mean, I think the exercise that comes later makes you plot something else. Yeah, plot the top 20 and show the gene names. So because 20 genes are going to be readable. Good. Yeah, well, gene names is using too much space, right? Yeah.
Reduce the font size.
Yeah, we could, or let's not show it.
If we remove the column names, then I cannot like.
These are not the only options within pretty heat maps. You have a lot of different options. Actually, there is one that is file name. So if you give it a file name, you would save it as that file name. So what happened now with the class train, right? We don't get that nice separation. So if we do a PCA with only 20 genes, similar situation is going to happen. We're not going to have good separation of the samples. So the 20 top genes doesn't explain the whole story either, right? And don't run this section. I think we can skip it. We don't have to run this, just in case it takes too long. Doesn't anything that would take long? I don't know, I'm worried that accessing this would take a little time, but let's see. Don't run it. Let me try first. Oh no, it's fast. You can do it. Just in case. Should I move on? Still people trying to plot the heat maps? We'll have more chances to plot more heat maps down the notebook. I mean, while we wait, spend some time here trying to understand what we're doing. Everything good in this side? Seems so. Okay. I mean,
This is the data of normalized way.
yeah, we're asking DDS, give us the counts, right? And we ask them how, normalize, row or not. So probably if you say false here, you're going to get the row counts. But we want the normalize, right? And this goes here, right? So basically we're asking, give us a data frame. That's the structure of R for tables, right? And we store it in normalized counts. What about here? What are we doing the second line? Any guess for the second line?
We are defining the row names, rows.
We are getting the row names, which are this, right? And what are we doing here?
Gene word is the
We're creating a new column. Remember, this is the symbol of column to access columns. If this doesn't exist, it's going to create it. And we're assigning the row names to a column.
what is the gene there?
It's the name that I give it to the column. Did I keep it? Did I do something with it? No. I created a column, so if you, well, we don't have to do it. I created a column called gene. You can give it any name you want. Just it's arbitrary gene name. I mean, this is also pretty readable, right? Yeah. So basically, we are separating the column we just created in two new ones, called ensemble ID and gene symbol, by this pipe. I know this forward or backward slash, I always get confused how to call them. They are necessary because the pipe could mean something else. So just to be sure, we're telling this is the pipe symbol, basically by this pipe. We're splitting this into two new columns, one called ensemble ID, the other one symbol. And then, so we have this table, and we rewrite the table with these new two columns. This is what we told you before. There's that library called OpenXLSX, so XLSX. And what we're doing is just storing the count data in this file and giving a name to that specific sheet.
So this is for Excel?
Yeah, if you want to create Excels in R, this is a way to do it. So I'm storing a data frame inside of here. That's the short story about it. Oh, finally, we've arrived to differential expression results. Okay, the way to access the results is just calling results into our object, to the DS object. We have an example here. So this is the third step. So if you want to summarize, and I think I've done it at the very end, we created one object. We give to the DDSig2 our data with the count data, metadata, and our formula, right? Then we ask DDSig2 to do the analysis. Actually, our third step would be access the results. With these three lines, we've done the analysis. Everything we've done between the beginning and here, it was just exporting the data. DDSig, I think it's the vignette we recommend. I don't remember what I read it. So you can actually specify the alpha you're going to use for filtering. They recommend it because it's used internally for filtering genes that are not important, right? Where we said there's an independent filtering process that I'm explaining here. And I don't know if we need to go into many details, but internally, DDSig2 makes a decision about genes that are very low expressed. I'm not doing anything in your analysis. And to some extent, it's important to filter them. And well, if you read, you're going to know why, just because of this. So the more tests you do, the more adjustments you're going to have to do to your p-value, right? So when you do analysis or a statistical analysis, right, you generally say, oh, I'm doing this t-test, right? And if it's below 0.05, I'm calling it significant. We are doing 15,000 tests. Let's assume we don't filter anything. We have 15,000 genes. We're going to do a test for every gene. So just by random chance or by definition of the 0.05 false discovery rate, what we're doing is assuming that 5% of the time, we're going to have a false call. So 5% of 20,000 genes, how much is that? 1,000, 2,000? No, 2,000 would be 10%, right? So 1,000 genes are going to be called we're going to call it significant when they are not significant. That is why we apply correction. When generally we do a lot of tests, what we do is to apply some sort of correction, right? We call it false discovery rate, Q values, p-adjusted values, depending on the technique we use. So if we remove those genes that are useless because they don't have any, the count is too low, they're zero, we don't have to do a test. So the correction is going to be lower. So one of the reasons why we do the independent filtering is called is that. So we want to correct for that. In any way, they're going to have a very low count, and they're not going to do anything in our analysis, and we don't care about them. And if you really care about how it's happening, the independent filtering, there are some options that you can tweak if you want to. And so if you read the manual, I think it tells you how to do it. I generally leave the default. I don't think you need to mess much about that. So
Sometimes it comes true and false in the data, or the false discovery rate is less than 0.01. So,
So if you want to be more stringent about your false discovery about your alpha, you can reduce it when you do this. You can change it here,
to 0.1.
for example, if you
So
want to.
otherwise the 0.5 is sufficient
Yep.
for the.
I'm assuming, I don't know if there's a default in this value. Maybe the default is 0.05, but there's nothing bad or being explicit about what you do, right?
So we should
So changing the
remove.
0.05 changes the way that independent filter
So
works.
ideally we should remove these genes if it is false discovery rate is less than 0.05.
No, you don't have to remove that.
Okay.
So
If we are doing data manually, like here we are giving command. So if that we have data and it's showing false discovery rate of less than 0.05.
no, that was when it would be significant, right? That's your p-value, your adjusted value.
Sorry, I didn't.
No, this alpha is the cutoff that you use to say if it's significant or not,
Okay.
right? In statistics, we call it alpha, right? The p-value, alpha, p-value. So exactly, it's the p-value. I don't know why. Yeah, it's better to call it p-value. So this is going to be the cutoff you're going to be using. So if you know you're going to be using 0.05, it's good that you do it or you indicate it when you access the results. So again, the only thing we're doing here is reading the results from this table. We are not recalculating anything. Again, I'm using head here to obtain the top of the table. The results table on DD6 already tells you what you are comparing. It tells you your condition as lead deprived versus normal. It uses the wall test. Sorry, I didn't give many details about the test, what is used, but that is part of the type of analysis we're doing. This is not a t-test or anything like that. We're using wall test because we're assuming it's a binomial, negative binomial distribution. That's how it's normally the gene expression data is distributed. We have a bunch of columns. I'm assuming a lot of you are familiar with them, right? The fold change. I don't have to explain much what it is. Log2 fold change. This is log2 fold scale. This is a log2 fold change, a standard error. This is a statistic of the wall test. The p-value, and this is the p-adjusted value we were talking about, right? So if you do multiple testing, you need to correct for multiple testing. So this is the p-adjusted value, and it uses the B and H, it's called, no? The Benjamin Hort correction. So this is how we corrected this p-value. So now you have the results. So you could do any filtering with them. You can download them, have it in Excel. If you do summary results, you're going to obtain something like this, and already it's telling you out of this number of genes, these are the ones that are significant with positive values, with a positive fold change. These are the ones that are not significant with a negative log2 fold change.
But they together make up around 40%. What happened to the rest? Like there are 8% because of the
So the 60% or the 59%, it's not significant. They are non-significant. So these are only the ones significant with a p-value, adjusted p-value below 0.05.
So those non-significant will then not come into the list.
No, they are in your list. So they are in your table. They are here. So for example, this one, this is 0.95. Or this one, this is 13. These are non-significant. This is just a summary of the table on top.
But then can you put a command in that tells you that, okay, show me only the...
Oh yes, you can filter it. This is R. Once you have a table, you can apply any filter you want. Okay, so there's one more thing. You can still tweak a little bit your data. Are you familiar with the MA plot? So the MA plot, I think it comes, I remember used them already with microarray data. I don't remember what MA stands, but I think it's for the old times. They kept the name. So basically here what we're doing is, so the mean of normalized counts on the x-axis and the fold change here. So basically these are the highly expressed genes and the lower expressed genes. And you can see in the fold change, there's a lot of variability, right, compared with the higher expressed genes. The blue dots are the ones that are significant. Yep. So if we want to plot fold changes, we want to sort by fold changes, we're going to be biased by how much variability are here in low expressed genes. It's really hard to tell if you have a count of 1 and a count of 10. Yes, so the calculation may tell you it's 2 times more expressed. Is it? You don't have much information. Really, you have that much information to be precise how many times it is? It's different if you're working 100 levels, right? You're going to be more precise about the fold change in here than in lower counts. So there's a way to correct for that if you want. This is not only going to be important for plotting fold changes or if you need to sort them by fold change. So there is a process. Well, I'm already answering the question, sorry. What do you notice in the MA plot? So that the variance of fold changes is higher in lower counts than it is in higher counts. So there is a function in DSIC2 that is called log fold change shrink. That function, what it does is to reduce the effect of the lower counts to make the fold changes for lower count genes smaller. So basically, you provide the object and your result table. I think it's better if you do this. And there are different types of shrinkage. So in this case, we're going to use this one. But I mean, there are others. You can read about them.
So it will remove all the low count genes with having higher
No,
fold change.
we don't remove anything.
No, it's not removed.
No, we don't. At this point, we're not removing anything else. We just have a table stored in this variable called res. Right? If you go up, Yes. Yeah, okay, it works.
Sir, which is battery is low, sir.
I don't know if it's low. It is working. If you're going
No, sir. Red light is blinking. Na?
Oh, okay. Take your time. I don't like the mic. Okay, save it. I mean,
It did not.
It didn't happen.
what do you mean it didn't happen?
One more row is missing. One more column.
I didn't touch anything. I mean, I ran my code. You have my code. It should be the same.
No, it is not coming in two tables.
Gene ID and sample ID, they didn't separate in the next table, the neat one. He said one more column has been created.
Yes.
Okay, okay. At the end, at the end. Okay.
Okay,
Yeah.
okay.
So save it to a file. So now you want that table in your computer. Maybe you want to use Excel for filtering or for whatever reason. So you can save it to an Excel file. Anybody has a questions? Am I going too fast? Too slow? Stop me, ask questions if you think I'm going too slow.
Just right pace.
Just right pace? Okay. And again, if you can always read everything I'm saying, I'm pretty sure is there. I don't think I'm not saying anything new or not present there.
Can this all material be downloaded? Like what you have put in the,
Say it again, please. I didn't hear you.
like the all the material of all the days can be downloaded somewhere? Like
Everything we're doing, so I don't think it's worth to download these results we're having now, but the Jupyter Notebook will share it for sure. Yes. We're placing some disk space. You can download it or send it by email. We figured out a way to share it, like Google Drive or OneDrive. We create something like that to share everything. Yes.
how do you save this in a Excel file?
There is an example a little bit above this. We ran already one example. We saved the normalized count in an Excel before. Oh, and to give another example how you can save it, because it's how we call fine with uppercase, right? Um, don't copy me. Do it yourself. I'm gonna call it like this. No, don't copy me. No, I'm gonna wait. So I'm not. If I ask something, the solution is already there. I'm not asking anything new. Here you have your answer. We've done it before. And I think the next time if I use this Jupyter Notebook for something, I'm going to correct everything so we use pipes all the time because I think it's more readable. But okay, good. I mean, something like this should work. I think we give it more options in the other one, right? What do we give? Oh, we give the sheet name if you want to. Sure. Sheet name was like this. Don't copy me. Why people copy what I do? I mean, it's as simple as this. You don't have to give more options, but you could. I think there is an option that you can give one argument that allows you to freeze the first line, the headers. I think it's really practical, but I don't remember how it's called. It's called freeze. It's freeze. Freeze it. You need to indicate what row you. I mean, I don't know. I'm gonna try this. Oh, it works, but I don't know what it does. Let's see. Don't download anything, okay? I'm just showing the results for you, but you don't have to download anything. We are not going to use the Excel for anything. No, it didn't freeze anything, right? No. That option didn't work. I don't remember how it's called. ChatGPT it and see if you find it. So you don't have to download anything. Don't download it. I'm just downloading to show it to you. So if you save it as an XLSX, you can open in Excel. You can apply filters however you want. If you like Excel to work in Excel, this is an option. You can do that. But you know so much R now that you don't need to do this. Look what I'm doing with that. Okay, next step. We're going to improve the volcano plot that Bonnie did yesterday. using the enhanced volcano. Well, we improve it to some extent. So I leave it flat, but we can, if you change the options, you can make it nicer, just extending it vertically. Well, we can make it nicer, but so we change the options in the display. So we can increase this. Oh wow! But I made okay. Let me wait. Way too big. Sorry, I need to make that. Sorry for the people in the back. You can change the options for enhanced volcano. You can make it as wide as you want, as narrow as you want. There's a lot of options you can play with it. I don't know if you remember this gene. This is the one that was the top one in the loading for PC1. That was the one over there. Probably those ones are over there here too. So do you know how to read the volcano plot? I don't know if Bonnie mentioned it. So basically what we're doing here is plotting every gene, the fold change of every gene. Right? The ones on the right side are positive fold changes. You have the 0 here. The ones here are the negative fold changes. And here you have the minus log 10 of the p-adjusted values. And we are creating some cutoffs, right, with the vertical lines. This is the log 2 fold change cutoff. And then we are coloring depending on if they are in the mid section or the right section of those. So these are going to be the top most differentially expressed genes, and we have them on the positive side. It seems that we don't have any reduced expression below log 2 fold change on the left side, right? So this is a good way to summarize the whole table in just one plot.
So the gene which is mentioned in the top, it is the most highly variable one. The plin 4.
The plin 4, I don't know, it's not necessarily the most variable, but it's the one that has the highest fold change and the lowest p-value. Yeah. What I mentioned about it is that it was the gene with the biggest loading in PC1. So the one that was set, PC1 was the one separating sleep deprived from non-sleep deprived.
So it is the gene which is required for the storage, significant storage and breakdown of fat.
Okay. So is sleep deprivation affecting the fat storage? It could be.
People who lack sleep, they are usually obese.
Yeah. Okay. Yeah, I heard that before. So that I think plot counts is from DSIG2. So this is the gene that we're talking about. You can just plot it with this function here and separate it by our condition. And you can see that is a big difference, right? Not only a big difference, but also really tight expression, right? We're pretty confident about the variability within groups that this is really significant. Okay, let's practice a little bit the piping and selecting genes and filtering. Can you answer these questions? Using filtering. So try to answer the questions using filtering. So for example, store the significant genes in this variable. Store significant genes with a fold change of 1. I said here, yeah, fold change of 1 in this one here. And then use these genes to plot a heat map. So the genes that are here, use them to plot a heat map. Remember, to plot a heat map, we are using the, how we call it, RLD data. It's not our original data, it's the log normalize. Sorry, R log transform, not normalize. I'm already giving you half of the PDHAP function, so basically you need to indicate what we are plotting here, right? We're missing an argument, the main argument. We've done some of these operation of selecting. What else we use? I don't know, we use other ones. I don't know if we need anything more than selecting. Oh, filtering. Filter and select may be enough to do all this. I'm not getting away with it. Damn it. So if I do this, in the volcano plot, previous volcano plot we had, I'm going to change the title. Right? So all the red dots are 111. So my question was how many red dots we have. Not only the ones on the right side, I want both sides. Do you need to change the colors for the downregulated ones? If you want to change them, you could. I don't think you need to. I mean, you have the legend on top, the legend, the only thing. Right. The legend tells you blue are the ones significant, red are the ones that are significant and are above the threshold. That's what it means. So how is the news heat map? No? Okay, good job.
I copied Bhumi's.
Exactly. I mean, this you haven't even. Oops. So again, I'm not saying anything new. We already plot a heat map, right? What is it? The easiest thing. I'm giving you tricks how to answer the question. So we need. This is the information we need, right? But instead of the top variable genes, we need to provide. So you can even come here, copy this. Come on, we can do it. You should have something similar to this. You have less genes, right? I noticed.
Yeah, it is actually top variables. I didn't change it to genes FC1.
Oh, okay. Oh, you didn't.
What is gene FC1?
You just created that a moment ago. What it is?
Okay, okay.
What is genes FC1? Is it this? After filtering and getting the row names. So these are the row names of the genes that have a p-value significant and an absolute fold change bigger than 1. That's what it is. So this is our transformed data, and I'm asking getting the rows for these genes. I don't care about the rest. And do a pretty heat map. That's what it is. So that's what I was saying about that paper. That paper showed 10 genes. And if you do the clustering, right, you're selecting genes that create differences. So it's expected that you're going to get a good clustering because we are selecting the genes that are different, and you get a beautiful separation, right? And you have really blue section, really red sections. You're selecting genes that are already creating that difference. Okay, summary, right? To do an analysis in this seq2, or sorry, anyone have questions? Period heat map questions? No? Should I move on?
We are getting error.
I'm going to wait. Okay, I wait.
So we have to annotate, right?
You have to annotate.
In the heat map.
Um,
So our heat map is showing error and the argument mat is missing.
um, yes, that's what I've been saying from the beginning. You are missing an argument here. That was the only thing you needed to add to plot it.
Yes.
You need to provide the matrix, right? So I'm going back again.
So we have to SA and the fold change
So
value. Yes.
no, not the fold change value. So here, What is in here?
The fold change part.
No, no, no.
Genes with fold change part, no?
Yes. The gene names, the raw names of the genes that have a fold change bigger than 1 and are significant. So I'm selecting, again, I'm the square brackets around a matrix of data frame, right? I'm selecting the rows, I'm giving the names of the rows that I want, and I want all the columns, because I'm not selecting columns after the comma. We already done this before, the pretty heat map. So what I was asking is you needed to fill the gap here. We needed to give the data. Are we good? So a basic analysis, if you don't do any exploration, right? We can summarize it only in 4 lines, or even in 3 lines if you want to. Right? With these 4 lines, you have a full analysis in DSeq2. Without exploring or plotting anything, you could summarize the whole day like this. I'm going to ask you to do the exercise just below. Again, you only need these 4 lines. You don't need anything else. You can do the exercise below.
Okay. We'll give an exercise. Given that the square of C genes are there that C1 are there, comma other D square bracket and D4 plus minus D4 formula.
She's waving.
बस वो सिर्फ वो ही वाला मिसिंग था वो हमने सेलेक्ट नहीं किया फिर उसमें कौन सा डेटा से हमें ये हीट मैप जनरेट करना
वो डेटा तो आना चाहिए ना,
है हाँ
हीट मैप वाला हम जिसका भी डेटा
जीन
देंगे विद द फोल्ड चेंज।
I mean, in our metadata, we created this column. We can have call it anywhere, anything, anyone, anything you want. We could have had something like treatment, and still have 4 different levels of treatment. I will insist a little bit more if we have time about how to define the design and the formula. Okay, have you tried to print the top 6 lines of the results? Say, what do you see different here? What is the problem?
It's showing the same, I think, because that was also 1116. Here we are,
Good point. Good point.
it's showing the same data. So
Is it
we,
showing this? No, it cannot show the same data that I'm thinking of.
so the average is
Well,
coming,
the base mean is the,
base mean is
because it doesn't matter how you do it, it's going to be always the same.
so here is wild type sleep deprived versus wild type normal. Earlier we had wild type normal.
Earlier, we classify all the samples without considering the genotype between a sleep deprived and normal. Here we split it in 4 groups, right? So here, the main problem now is that we only obtain the results for 2 of them, right? In this case, only wild type. Why? Because we define the levels to be wild type, our baseline, right? And the rest gets less important. But, I mean, you have 2 options. You could relevel everything in a way that you can see the comparison you want, but you don't have to do that. So everybody reached this point? Yes? The background too? Good. Did you see the problem now that we have? That we have 4 levels in our treatment, right? We have wild type as normal, wild type as sleep deprived, knockout, normal, knockout as sleep deprived. And when we access the results, we only get one of the how many possible comparisons? Whatever. If you do pairwise comparisons, depending on if we change sides or not. But we can have a lot of comparisons, right? But we only get one. So let's imagine that we want to access the same comparison between a sleep deprived and normal, but within the knockout. So there's ways to do that. And that's the next step.
So if we use the condition here, so it's taking by themselves that wild type sleep deprived oblique normal here, but we have given just geno condition.
And that's enough for the analysis we want to do. You don't need to give anything.
It's not analyzing all the groups.
Yes, it's analyzing all the groups. So everything you've done so far, it analyzed all. So inside of our results object, not inside of our result object, inside of DDS, you have all the results of all pairwise comparisons.
But it's not visible here because we have chosen head for the.
No. Don't go ahead. You have how to access here. The answer is all this paragraph. So the question is, they ask me, do the results contains everything, or the DDS, right? Because we are only obtaining one of the comparisons. So if I go to DDS, so our DDS object, how we access the coefficients. Remember, we can access, I thought it was not coefficients, full name, right? It wasn't coef. Now I don't even remember. Like this. Oh yeah. Okay. So if I access the coefficients, so our fold changes, everything is here already. Or almost here. I mean, the DDS object doesn't have the p-values, the q-values for all the comparisons you can do, but they're easy to access, right? So we can use the contrast. You can request, you're not going to use condition in this case. This is just a general example. You're going to call the column that you want, and you're going to ask, comparing whatever you want to compare against another thing. And that way you're going to get the results tables that you want. This is, for me, is the easiest way to access. There's a different way to access the results, but I think this is the easiest. You already indicate the column we are analyzing, right? But you're going to have to indicate it again. So this is what we want to access. And you're going to compare, I don't know, let's access what we said, the knockout, the sleep deprived versus normal. So that's what I am asking next, right? I'm asking something like this. So do this. I'm assuming we are missing something here. Oh yes, of course, we're missing you need to fill the gap between these parentheses and fill the gap between this, and then this is complete. Right? This is just defining what is in that column. It's even better if we do this, right? These are the 4 levels that we have in that column. Before we only had sleep deprived and normal. Now the problem is we have 4 levels, so there are a lot of pairwise comparisons that we can do here. So what I'm asking is this. Use contrast, as I explained earlier, to access this comparison and plot an enhanced volcano. You don't have to touch the enhanced volcano, but you're going to have to fill the gap here and here. So we are able to run this without an error and plot the enhanced volcano. And the answer pretty much is just about this. Again, I'm not asking anything new. You just need to apply the same logic, that the example that I'm giving above. Did anybody plot the enhanced volcano? Not yet. You don't get T until you finish this.
The tea is ready, actually it's boiling.
Until you get the enhanced volcano, you don't leave this room. Did you guess this? I guess you did, right? I mean, read what I wrote before in the paragraph before. It's explained. It's there. There's no magic here. What about the shrinkage? We did it, right? You have it here.
I got the results for Canada.
Don't copy this because this is wrong. Okay.
So I got the 21224.
You got what?
No?
You should get a plot out of this if you run this. It's the answer of the universe. I thought it was 42.
Nobody gets the chance.
L11 data analysis को कोई नजदीकी ह्यूमैनिटीज भी कर लेता है मुझे लगता है
I think I'm gonna have to change this. Sorry. Do you get something like this?
Wait. Now I'm getting it.
No. You should know by now.
So mine is input plot.
So there's a different way to access the results. So these are the coefficients of all changes already pre-calculated. They are stored in these using these names. So if you want also quick access and the comparison is already be pre-calculated, you can use the full name instead of this long contrast. But not all of them are defined, and I'll explain that maybe if I have time later. But yeah, to resolve the exercise that we're asking, you needed to fill this line and this, and it would plot a enhanced volcano. Any questions? If you read, the answer is there. Don't follow the screen. You pretty much have explained how to do this.
We have to run actually.
The above line will you don't figure out.
We've done it before. This is Rickage. I mean, you don't have even to do this. You could skip the second line and still gonna get a similar volcano plot. It's not gonna be that different. So if you notice, our favorite gene is still there as one as being highly differentially expressed, right? Positively also. So within the knockout, clean 4 is still important between sleep deprived and non-sleep deprived. So if we plot that gene, and we separate the data between the four conditions. What you can tell, right? So PLIN4 is important for the sleep deprivation, but it doesn't matter if it's knockout or not. If it's a knockout, the gene still is going to create big difference within normal and within the knockout.
What is third? What is third? You wrote shank normal and
Oh,
shank.
what is missing?
Shank is sleep deprived. Shank is sleep deprived, isn't
No,
it?
No, normal,
like
right? Oh
but
no, normal it is here. Sorry, which one is?
shank 3
Shank
normal.
Ah,
three sleep
you're
deprived
correct.
and
Sleep
not that.
deprived. Yeah, yeah, exactly. The sleep deprivation in
It's
Shack 3.
not, the shank is not playing much role.
नहीं, it is not being displayed, but ऊपर है ना
No, no,
left.
मैं समझ गई, but it's not because the biphasic is also coming.
This gene is barely affected by the genotype. They don't care what genotype it is. It's only affected by being sleep deprivation. So before we have T, one thing that is really important, citing, I guess, if we're going to cite the paper, but this line here, let's print it and you see what it does. So it's quite common in Bioconductor and maybe other packages that if you request the citation of a package, they generally generate the citation for you so you can cite it in your publications. But this one is quite important too. The session info, what it's doing is describing all the packages that you use and what version was used, right? So if you need to come back and somebody tells you, oh, what DSIC version did you use? You already printed, you save it, it's in your document, so you only need to check it. Why we put it at the end? Why we print the session info at the end of the Jupyter notebook?
So like everything you do can be captured basically.
Yep, that's the idea.
For the reproducibility of further
Yeah,
analysis.
definitely, but we do it at the end, as he said, because let's imagine we load the libraries at the beginning, but we could have load the library in the middle of the code, right? So we want to wait until the end to print the session info. If I tell you the truth, I barely do that because I always load my libraries in the top, but it's always a good practice to put it at the very end. And the notebook is done, and you can have tea. Questions? Questions, problems?
Guys, tea, tea is ready. Whosoever wish to have tea can go out and have tea. Because they close the tea counter by 4:30.
So just one more thing that I didn't explain. So we are asking that column, right, in our condition table to compare this versus this. A positive fold change, sorry, how to say that? This is the numerator and this is the denominator, right? So the first factor, level of factor you're given is going to be the denominator, numerator, and this is the numerator. What is the one on the top?
Top is numerator.
Oh, top and bottom. So a positive fold change is going to be something highly expressed here. Sorry, I didn't explain that.
Usually we do suppose the disease conditions, the divided by the
Normal.
Normal, yes.
So that's
So this is the idea.
increase probability.
So this is normal. So I didn't
One will
explain
be
that.
up for this, it will be down for that. One will be down for that, one will be up for this.
So if you want the opposite, you change them.
No, no, no. Suppose ये मालूम है गलती से कर भी दिया पर अब मुझे पता है कि मेरे को वो डाउन शो कर रहा है मेरा एक्टिविटीज इन द लिस्ट में अप करेगा या
So the genes were down regulated to the list condition after updating.
हाँ आपने क्या
Can I?